All right. Is that recording?
First, we should build dorms for the bigger school.
Okay. So let's get started on the wedge lecture. All right. So good job. The first two rows, we're passing the homework. Good job. Okay. So 2 lectures ago, and I have to apologize with lab yesterday. I have 12 more tests to grade. I broke my streak. I apologize, but I'll be done. Got some size and some booze. I'll be done today, so I'll post your grades by early this afternoon. Hopefully before recitation, maybe not. I'll send you an email when that is. They're better than you think. Okay, I know the last one was hard, but your thought process, for the most part, was correct. So the average so far is the highest that I've seen from the first 2 tests. So you guys did better than you thought. Okay, because I don't test math. I don't care about math because once you have a PhD, you can't do it. So, what's that?
Has there been a perfect score?
No, not yet. Okay. So, think back to last Friday. Okay, hang with me. Okay, last Friday. Okay, we mentioned the concept of or not last Friday, last Wednesday. Simple machines. Okay, we solved them with a holistic approach similar to frames. Okay, but the difference between frames and trusses and machines is what? Support versus transmit loads, right? Machines are designed to modify or transmit or change the input force. Okay, they're changing it through that mechanical advantage. Okay, so a simple machine in mechanics. Okay, they date back all the way to the Renaissance era. Okay, before we had any sort of technology, and they consist of simple machinery that are composed of one of these 6 simple machines. There are a lever, a wheel and axle, a pulley, an inclined plane, a wedge, and a screw. Okay, so if you recall when we started our machine lecture, I told you we're going to solve these individually. But before we solve them individually, we had to take into account one key component, which is what? Friction. Okay, friction changes machinery tremendously because your machines have to overcome that friction force. Okay. So that's kind of why we have that divide between modules. We have machines in module 3 and we have simple machines in module 4 because we have to take into account friction when we're analyzing these machines as a whole. Okay? So today we are going to be focusing on the wedge. Okay? Just a simple wedge that drastically modifies the input force. Okay? It's a small wedge used to move a load that is tremendously larger than it. All right. So thinking back to your machines, how do you solve machines, just as a whole? What do you do with each individual component? Free body diagram. Okay. Remember that when you're analyzing a machine, okay, you're separating out each component and you're analyzing them individually. You're applying your equations of equilibrium to each individual component. Okay, so I'm going to go through a short derivation here to describe the input force and how it's actually changed. Okay, so stay with me, but it's also going to be teaching the method of solving wedges. All right. So when you're solving wedges, your first step, okay, is to draw the FBD of a wedge with the known force applied. Okay. So we have our FBD with our known force. Okay, so in this case, this is going to be that wedge on the bottom, right? We're applying a lateral force, F, right? So if I draw my free body diagram, okay, I'm going to take the easy forces and do those myself. We have this known force F and the weight of the wedge. Okay. And I want to stop here, okay, and back up a little bit from what I said on Friday when I told you that in statics the direction of friction doesn't matter. It only matters in dynamics. Okay. That's still true, but when analyzing wedges in simple machines, you need to take into account the dynamics of the system. Okay. So with simple machines, the direction of your friction force matters. Okay. And that is because the direction of impending motion, excuse me, the direction of impending motion will affect the friction force because friction does what? It opposes motion, right? So if we know that this wedge, okay, is going to be moving to the left, okay, I will call that impending motion. Okay, we are analyzing this at one instance of time, okay, but the wedge is designed to lift this load, okay? So we are at this point in time when we're about to move, so we need to take into account the dynamics. So a friction force is opposing motion. What direction do we draw it? Opposite of the motion, okay? So we have a friction force acting between the wedge and the ground. I will call that mu p, and a normal force from the weight of the wedge and the ground that I will call p. Okay, this mu p is Coulomb friction, okay? It's my friction force at p, okay? Fp and p are not two different unknowns because they share the same normal force. Did you all pick up on that in your homework? When you're solving it and you apply your equations of equilibrium and you see you have 6 unknowns? Okay, well you don't really, because p, the friction force at p, shares that normal force. All right? So we also have a normal force, or a friction force, okay, on the surface of the inclined plane, okay, and it's opposing motion. So I will draw it up and to the right, and we have a normal force from the weight of the load onto the wedge. Okay, so we have to take into account the direction of impending motion. So this is the only time in engineering when you get to look at a problem, okay, and use your intuition. You need your intuition, because it no longer holds that we can slap our forces on there and our math will tell us what's wrong. Because if we draw our friction force to the right, what is that actually doing in the system? It's assisting the motion, right? We're getting help from friction, and that doesn't make any sense. Okay, so this is your green light. Okay, when you see these wedge problems, to look at your intuition, to use your intuition, because you have to overcome the friction in your direction of impending motion. Yeah, Drew?
So I guess I'm confused why you chose that sense from UN. Because wouldn't the little block, as it's moving, there's motion in this direction, wouldn't the friction oppose that motion?
So Drew asked, why did I choose the sense of mu n? Okay, and then you said?
Well, there's the big block and then the little block. So the big block is moving up like that. And
But we're not taking into account the big block. Okay, so Drew's thinking collectively, okay, and that's easy to do. He's thinking collectively of how the system moves, okay? But the wedge, okay, just this wedge is moving to the left. Okay, so friction force, even though we're on a surface, needs to oppose that, right? And to counteract that horizontal force, right, there is some rectangular components that take into account. Does that make sense? Are we okay with that? Okay, I want to make sure we are, because I had Friday brain and I spoke a little too soon on Friday. Okay, so impending motion is the language that we'll use. Okay, and I think it's handy just to draw it so you can make sure. Okay, so we've analyzed, okay, one block, right? We've applied all of our forces, known and unknown. Okay, and now we're going to move on to the other components. Analyze them individually. Right? So in this case, it is the load. Right? And I'm going to take the easy force away, and we have our weight. The weight of the load. Okay? What direction is the impending motion?
Right.
Of the load. Okay? Think about it. Say it with confidence, Curtis. Chase. Dang it. Curtis, blonde hair, come on. Curtis is so disappointed. Just couldn't be more mad. It's upwards, okay? We're using a wedge, we're sliding it up, okay, to apply an upward force to move this this load in the vertical direction. Okay, so if my impending motion is upwards, okay, how do I draw, what direction do I draw my friction forces? Downwards, okay? So we have this friction force between the wall, that vertical wall, and the load. Okay, we'll call that mu q. Okay, and if there is a friction force, there is also a normal force, q. All right. What direction do I draw the friction force on the load on this face? Okay, down and to the left. Okay, even though we're on an angled surface, our impending motion is still vertical, so we need to counteract that in the negative j direction. Okay, so I will call that mu n. We also have our normal force. Okay, so guys, stay with me. Previously, okay, we drew them equal and opposite. Okay, we drew them here, and then we knew they would be equal and opposite. But because our directions mean something now, that inherently will do it for you. Okay, so we could start with the load. Okay, and if we draw our friction forces with the direction of resisting motion, of impending motion, okay, we have our wedge. Those forces will be equal and opposite. Good job, Will. Thank you. Thank you. He got up. Okay, does that make sense? So we have all of our unknown forces on here. All right, so now what? What's your next step when you're analyzing anything in statics? Who doesn't know what we're solving for? Okay, so it's not written on there. Okay, we're solving, I want to know how the input force is changed. So I want to solve for F. Okay, I want to derive the expression for F and how that's changed. Okay, so to do that, what methods do I use? What's the only method in statics? Equations of equilibrium. Okay, so if I start with the wedge, do I need to separate you two, or do you have a question?
Oh, I was asking me what was on for F specifically, like, and then she answered my question.
Okay. So if we start with our wedge, we apply our equations of equilibrium to the wedge. Okay. If I sum the forces in the x direction, okay, what's in there? What do you think, Sergio? Sum the forces in the x for me.
You have the n,
yeah, there's one component on the end, one component on the top friction, the right force.
We have one component of the n, so let's start there. Okay, so we have n. How do we get that in x? In an x component? Sine alpha. Good job, Zach. Sine alpha. Okay, then Sergio said we had a component of mu n. How do I get that in rectangular components in the x direction? Cosine, so plus mu n cosine alpha. Okay. What else? We have f minus f. And then plus mu p. Awesome. All equals 0. And if we sum the forces in the y, okay, what's in that equation? What do you think, Will? This Will?
It'll be the normal force, so it'll be n cosine.
Mm-hmm. And cosine alpha?
And then it'll be mu n sine.
Say it loud, Zach.
It would be a negative n cosine alpha.
It would be a negative n cosine alpha because we're pointing in the negative j direction, the negative y direction. Okay? So n cosine alpha minus, okay, what'd you say?
And then it'll be mu n sine alpha.
Uh-huh.
And then it'll be plus the
plus P.
And then, oh yeah, and then minus the weight.
Minus the weight. Perfect. Okay, so I'm solving for F. Okay, I want to get an expression for F, okay, in the sense with we have no unknowns. Okay, so in friction problems, we're going to assume that we know our coefficient of friction and we know this angle alpha. What we don't know is P, Q, and N. Okay, so I can do some algebra here to get rid of a couple of them, right? Stefan, you look like a deer in the headlights when I said that. Okay, so it's a derivation. I warned you ahead of time. Okay, it's a derivation. So if I want to get rid of an easy unknown, we can get rid of is P. Okay, if I multiply this y equation by mu, okay, and subtract these two equations from each other, because I have a positive mu p here. If I subtract that from this equation, I can negate P, okay, and I will get my force equals N times 2 mu cosine alpha plus mu squared sine alpha plus the weight of the wedge times mu. Okay, we still have an unknown. We have another unknown of N. Okay, but I have another free body diagram, so I can apply my equations of equilibrium again. All right, so if I sum my forces in the x on the load, okay, what is that equation, Nick?
On the load,
Q, Q minus mu n cosine alpha Q minus mu n cosine alpha and the normal force. Okay, so putting that in rectangular components, we have minus n sine alpha equals 0. Okay, we also have some of the forces in the y. Okay, what's in that, Summer?
The weight of
Minus WL
and then the y component of n, so n,
plus n cosine alpha,
and then your friction down.
and then our friction down minus mu q. What are we missing? And then we have a component of the other friction force. So mu n minus mu n sine alpha equals 0. All right. So I can easily get rid of q here, right? Because I need to find an expression of n. Okay, in terms of all unknowns, so I can plug it back in here. Okay, so getting rid of q, if I multiply this equation by mu, okay, and then adding them together, because we have a positive mu q here and a negative mu q here, okay, you get, okay, n times cosine alpha minus 2 mu sine alpha minus mu squared cosine alpha is equivalent to the weight of the load. Okay? So I can divide all of this, okay, over onto the right-hand side of the equation and get n equals WL over this, okay, in which I know everything. Even though we're in variables, but we're getting better at that, right? Because my threats of dynamics are being heard. Okay? So we know alpha, we know our coefficient of friction. Okay? So if I solve for n and plug it in here, okay, I can solve for F to be equivalent to my weight of my wedge times my coefficient of static friction, okay, plus WL, okay, times all of this. So my numerator here is 2 mu cosine alpha plus mu squared sine alpha. Okay. And this became my denominator for n. Okay, so I have cosine alpha minus 2 mu sine alpha minus mu squared cosine alpha. Okay, so I have this expression for f in terms of everything we know, right? And that was our goal. I can simplify it down a little more, okay, which will help for the questions. So I have F equals my weight of my wedge times my coefficient of static friction times WL, okay, times 1 minus mu squared tangent theta, or alpha, plus 2 mu over 1 minus mu squared minus 2 mu tangent alpha. Okay, I just simplified it down furthermore. Yeah, Jack?
The equation that is 2 above the one that you just bought. You did
This
that
one?
by subtracting some of the forces in y from some of the forces in x.
Yep, we multiplied the y times mu. Okay, so we have a mu p. So we subtracted that.
So if I have an n sine theta on the top and then a mu squared n sine theta on the bottom,
Mu squared n sine theta.
do you follow me there?
Mm-hmm.
How do I end up with mu squared sine theta, sine alpha on the bottom?
Should be minus.
I'm wondering what happened. No, I'm wondering what happened to the sine theta on top, or sine alpha on top.
The sine alpha on top. Right here?
If we subtract the two equations,
Right?
we have, so up above that, so forces in x, the first term is n sine alpha.
Mm-hmm.
If we then subtract from that mu squared sine alpha, assuming both are multiplied by n,
Uh-huh.
which is the second term of the sum of the forces in y,
Mm-hmm.
why is it that we end up with mu squared sine alpha?
Mu squared sine alpha, because we are subtracting, we have a mu squared sine alpha here.
Yes, that you're subtracting.
We're subtracting
from sine alpha.
mu cosine alpha, sine alpha. Oh, am I missing a term? And 2 mu cosine. Probably missing a term. Or I wrote it wrong.
I think you have the 2 mu cosine alpha is correct.
2 mu
Then I think you should have a
times p
sine
mu.
alpha and then a minus mu squared sine.
Yeah, I'm probably forgetting something. Yeah, let me check on that. Okay, because I just coded this up. I'll check on that, but I think you're right. I think there should be another
Third line
mu cosine.
should be a sine alpha.
Yeah, let me check on that. Okay, and if there is a mistake, I'll post updated notes. Okay, but for the sake of the example, that's not going to change. Right, the sine alpha is only going to help us. Okay, thanks. That's always good. Okay, so write this down with an asterisk. Could be an algebra error. Okay, I'll let you know. We have an equation for f. All right. So what is this equation doing? What is it describing? With or without a sine alpha? This is our input force, right? So in your own words, what is that doing? What is that equation saying? Yeah, Erica?
The amount of force required for like motion to be impending.
Almost, kind of. Yannick?
So what the force is transferred.
Yeah. It's how that force, that input force, is translated into the system. Okay? So that input force, this is describing how it's changed, right? So in machines, okay, you use mechanical advantage to modify your input force, all right? So in this case, okay, if we were on a frictionless surface, okay, a frictionless surface in which our friction is 0, what do you hypothesize with this input force F, how it will be modified? Okay, well, if you plug in, okay, our friction force F, okay, and let's take this into a real world example, okay, a real world wedge, which is what? What is a wedge, other than just a problem?
Doorstop.
A doorstop. That's the most classic example. You have this small wedge, okay, with an angle, okay, an alpha that's relatively small. Okay, for example's sake, we're going to say an alpha of 14 degrees. Okay, I Googled, or I measured the doorstop and met. Okay, an alpha of 14 degrees, okay, in which our weight of our wedge is much smaller than the weight of our load. Okay, the weight of a small wooden doorstop in comparison to a door is extremely small. Okay, so we will negate that. All right, so if we are on a frictionless surface, okay, and we plug in mu, okay, you end up with your force is equivalent to WL times 0.25. Okay, and this is why I did this derivation, because I want this to bring in the conceptual understanding of wedges. So if you blocked that derivation out, that's okay, but pay attention now. Okay, we're on a frictionless surface of a wedge. Okay, how is this changing? What does this mean in your own words? In order to move the load, I need to. Yeah, Carson? Perfect. I only need to apply a quarter of a force equivalent to the load. Okay, but that's on a frictionless surface. That's never realistic. Okay, so if we have a coefficient of friction of 0.2, okay, you end up with your force is equivalent to WL times 0.75. Okay, so that input force is larger than it was on a frictionless surface. However, we still have a mechanical advantage because the input force is smaller than the required output force, which is the weight of the load. Okay, but what happens as friction continues to increase? Okay, if we have mu equals 0.4, you end up with your force is equivalent to the weight of your load times 1.32. Okay, and why is that increasing? Okay, conceptually, as friction is increased, okay, what does that mean about our, in your own words, what does that mean about our input force F? Yeah, Drew?
Well, I guess it's just that our input force F is being distributed and some of it is lost. Some of the energy you put in is lost to heat through friction, I guess would be.
Lost to heat through friction, yeah. You kind of combined all of the mechanics subjects, which is right. Okay, Peyton?
Your force, or your friction is getting larger, you have a larger force to maintain.
Yes. Okay, and you guys said the same thing. Okay, you have to overcome a greater friction force. Okay, so your mechanical advantage is quickly lost. Okay, because you need a greater friction force to overcome that. You need a greater input force to overcome that friction force. So that's why your machines, like in your car, okay, those are so well oiled because they need that mechanical advantage because it goes away so quickly. So when you ever get into any sort of machine dyes or an integration, right, you'll have that next year. Okay, design your machines with low friction. Right, Yannick?
If there was no friction, maybe it was zero, would the load just fall down and the load slip?
Not if we have an input force. Not if we have an input force. And if there's no friction and you invent that, you're incredibly wealthy. That's the dream, right? Okay, that's a good question. Yes, if there's no friction, because the weight of the load, depending on alpha, okay, if alpha is 0, it'll just sit on top of it. Yeah, Curtis?
.25 isn't for all angles of alpha.
No, I just plugged it in for 14 degree. All right, so a whole derivation just kind of conceptually bring home, machines are designed for mechanical advantage, and that starts with wedges, and we solve them individually. Okay, so let's do an actual example. All right, in which we have a wedge. We have two wedges with a large load sitting on top of one. And it wants us to solve for the force P okay, required to lift this 100-pound load. Okay, immediately, okay, before we even start, okay, is P going to be larger or smaller than 100 pounds? Smaller, why? Because that's the point of a wedge, right? It's a machine. It has mechanical advantage. And that means your input force needs to be smaller than your output force, right? So with machines, or with these wedges, okay, your first step, okay, is to draw your free body diagram of your individual components. Okay? And it's useful to start where you have your known force. Okay? And in that case, that is our wedge B, because we know that load that's sitting on top of it. Okay? So we're neglecting the weight. We're neglecting the weight of both of these wedges. Okay? But because they're sitting together, they're coupled together. Okay, the weight here is 100 pounds acting through, because that weight of each wedge is so negligible in comparison to the load. Okay? So our impending motion of wedge B is in what direction? Of this wedge here. Up. Okay? So our motion is impending upwards. So our friction force, okay, between the wall and wedge B is oriented downwards. Okay. You also have a normal force, NB. Okay. I reread the problem when I went to work through this last night in your notes. I was like, we can't solve it. We don't know the friction force between these two. Okay, I was solving it like that. I went back to the book, and they state that these rollers are frictionless. Okay, so that's just a simplification of the problem that makes it a little easier for us to solve. But make sure you write that down in your notes. Okay, so we have our weight, and we have our friction force between the wall and wedge B. Okay, we also have a normal force. Okay, because the weight of the wedge and the block B, okay, are applying a force, okay, onto wedge A. So then if I continue on, okay, so you can start with solving your equations of equilibrium. Okay, here, that's fine. Okay, a habit of mine is to draw the free body diagrams first, so I actually know what I'm solving for. Do what works for you, okay? But if I draw the free body diagram of wedge A, okay, you guys give this one to me. What direction is our impending motion? To the right. So what forces are applied? Two normal forces. What do those look like? We have the normal force of block A with the ground, right? And we have a normal force of the wedge A and the load. That's what you were talking about? N1. Yeah. We have friction force that is resisting motion. Resisting motion in this direction. We also have our known force P. Right? The problem says we're neglecting the weight. Okay, it's an assumption, but because these wedges are so small in comparison to the load, we're neglecting them. So if I apply my equations of equilibrium, which wedge would you start with? A or B? Who says A? 4 or 5? Who says B? Okay. Why did you choose B, David?
Well, because you have more focuses there that are known. That's right.
Yeah, exactly right. So if you choose A, that's fine. You're going to get your equations and you're going to solve for them. We can't do anything. So then inherently you have to go to force or wedge B. Okay? But it's a nice tool to start with the wedge where you have your known force. Your most known force is, in this case, our known force is that 100-pound weight. So if I apply my equations of equilibrium, we have some of the forces in the x. Okay. What is that equation? What do you think, Patrick? We have a normal force B I'm on wedge B here. We have our normal force N, N1. That'll be it? Okay. We need this in rectangular components, though, right?
Oh, so it would be
Okay.
so sine.
It'll be the sine theta. Okay, give me the positive negatives of those forces. It'll be a positive N1 sine theta and a negative NB. Okay, good job. So if I sum the forces in the y, what's in the y, Libby?
You have your positive NA, and you have your negative.
On wedge
N1.
B. On wedge B.
Oh, right. You have your negative USNP,
Good.
your negative weight, and your positive N1 cosine theta.
Good. N1 cosine theta equals 0. How many unknowns do I have? 2. Okay. I don't know NB, and I don't know N1. Okay. I have 2 equations. Okay. For the sake of time, okay, work this. Make sure you can get these answers. I'm just going to throw them up on the board. But I just solved a system of equations. Okay. Solving for N1, get 107.2 pounds. Solving for NB equals 18.6 pounds. All right? So then, we're out of time here. So then, you apply your equations of equilibrium to wedge A. Okay, and now our only unknown is what? P, because we know NA and we know N1. Or no, excuse me, we know NB. We can solve for NA, and we can solve for P. Okay, so what you should get P equals 50.3 pounds. All right, so work that, make sure you get it. Okay, I'm doing recitation today. Dr. Davidson can't do it. So I'm going to go over the last problem of the test, and we'll work through the second problem in our notes and potentially a homework problem if we have time. Okay?